Okay, let's dive right into this explainer. Welcome, everyone. Today, we're kicking off a full-blown investigation into the invisible magic that literally powers our entire world. We're going to put on our scientist hats, maybe even act like a bit of a detective, and explore something that we rely on every single day, but, probably rarely stop to think about. So tell me this. Have you ever wondered what is actually happening inside a torch or a flashlight when you flick that switch? I want you to just picture a simple flashlight in your hand right now. You push the button and boom, there's light. But try to imagine the hidden lightning-fast chain reaction that has to happen inside that plastic casing to make that light appear. It's like a tiny, high-speed puzzle. And that is the exact mystery we are solving today. But before we go prying open that flashlight, let's just take a quick look around us. Electricity is absolutely everywhere. It's this invisible energy that powers practically all of our entertainment, like your TV or the radio. It's the lifeblood of our communication, keeping mobile phones and the entire internet alive. It literally moves us around in trains and elevators, keeps our snacks fresh in the fridge, and even cooks our dinner in microwaves and toasters. We are completely and utterly dependent on electricity for almost everything we do. And honestly, that's exactly why understanding how this stuff works is just so important.
Okay, wait, quick pause. Before we start mentally building things, we have to talk about safety, because every real scientist follows a golden rule. The electricity that comes out of the sockets in your walls at home or at school, that stuff is extremely powerful and honestly very dangerous. Real scientists respect that danger. So for all of our experiments today, and any you do on your own, we are strictly going to use safe, portable power sources. Things like small cells and batteries. Never, ever, under any circumstances, use a wall socket for an experiment.
Now, here's a totally mind-blowing fact, a huge misconception we all have. You know that little cylinder you pop into a TV remote? Most of us hold that up and say, hey, look, a battery. But technically, just one of those all by itself is actually called an electric cell. A true, actual battery is a team of two or more of those cells working together. They get connected positive end to negative end to provide even more energy for a longer amount of time. It's kind of crazy when you realize how often we all use the wrong word for that.
All right, go ahead and grab your imaginary hard hats. It is time to transition into our build-it-yourself phase. Let's become engineers for a few minutes. I want you to mentally construct a path for electricity to travel from our safe little power source all the way to a lamp. Think of this whole process like building a super high-speed racetrack for energy. First up, we need to remove just a little bit of the plastic covering from the ends of our wires, maybe a centimeter or so, just to expose the shiny metal tucked inside. Then we take those wires and connect them to the positive and negative ends of our power source, our electric cell. And finally, the last step, we attach the other ends of those wires right onto the screws of a little lamp holder. And right there, that brings us to the formal, scientific term for our racetrack. It's called an electrical circuit. By definition, that's a complete, absolutely unbroken path that allows electric current to flow. So the absolute crucial point here is that if the racetrack is completely unbroken, the electricity successfully races from the starting line at the positive terminal, zooms all the way to the finish line at the negative terminal, and boom, it lights the bulb. So let's look a little closer at the two different moods or states our circuit can be in. A closed circuit means the path is fully connected, the current is flowing beautifully, and the lamp is glowing brightly on. But let me ask you this. What do you think happens if a wire snaps, or if the tiny glowing wire inside an old-school light bulb suddenly breaks? Well, that creates a gap, and we call that an open circuit. The path is broken, which literally stops the energy dead in its tracks. And the lamp? It stays completely dark. Now, speaking of light bulbs, it's pretty cool to compare the old school ones to the modern ones we use today. The older ones are known as incandescent lamps. They use that tiny little wire I just mentioned, which is called a filament. When electricity hits it, it gets so incredibly hot that it actually glows. And with those older bulbs, it really doesn't matter which way the electricity flows through them. But modern flashlights use LEDs. They don't have a filament inside at all. Plus, they have a secret trick. Electrical current can only flow in one direction through an LED. So to actually make an LED work, you have to match the long wire to the positive side of your battery. That is the absolute secret to success with those.
Now, obviously, we don't want to go around disconnecting and reconnecting our wires every single time we want to turn a light on or off, right? That would be exhausting. That is exactly why we use a switch. Just imagine a super simple homemade switch made out of a safety pin and 2 drawing pins. When the safety pin is swung open, it intentionally creates a gap in our racetrack. That's the off position. But when you push it so it touches the second pin, it closes the gap, and that's the on position. It brilliantly illustrates how a simple switch is basically just a drawbridge. Imagine tiny electric race cars speeding along. When the drawbridge goes up, they have to slam on the brakes. When it comes down, they zoom right across. It gives us total control.
Okay, let's move on to something that I think is super cool. All of this actually builds into an international secret code. You see, scientists and engineers all over the globe need to draw blueprints of these circuits. And to make sure that an engineer over in Japan can perfectly read a drawing sketched out by an engineer in Brazil, international organizations created standard symbols. It's literally a universal, secret language just for drawing circuits.
Let's decode the very first piece of the puzzle together. When engineers want to draw an electric cell, they use a specific symbol. Notice that there's a long, thin line. That stands for the positive terminal. And right next to it, there's a short, thick line, which represents the negative terminal. So whenever you see that little drawing on a blueprint, you know exactly where the power's coming from.
And check this out. Here is the symbol for an LED. The details on this one are so clever. Notice how the big triangle is pointing? It points exactly in the direction that the current is allowed to flow. Remember earlier when we said LEDs only let energy go one way? The symbol literally shows you which way. And those cute little arrows shooting off to the side, they represent the actual light radiating out from the bulb. Honestly, how cool is that?
All right, everyone, it is time for a game. Welcome to the Great Materials Showdown. Here's the setup. If we were to take the metal wires out of our circuit and replace them with completely random, everyday items from, say, your pencil case, which ones do you think will let the electricity through to complete the circuit, and which ones will just totally fail? Make a guess right now in your head. Would a rubber eraser work? How about a plastic scale? Place your bet, scientists.
Okay, let's reveal the surprising results of our test. The metal coin? Yep, it worked. The lamp glows brightly. But the rubber eraser and the plastic scale? Total, absolute failures. The lamp stayed completely dark. But hold on, look at the bottom of the results. The pencil lead. Now, pencil lead is made of a material called graphite. And believe it or not, it actually let the electricity pass right through. No way, right? The literal lead inside your everyday pencil can actually complete an electrical circuit. So the materials that won our showdown, the ones that stepped up and let the lamp glow, they have a very special name. We identify them as electrical conductors. Materials like silver, copper, and even gold allow electric current to flow right through them super easily. They basically roll out the red carpet for electricity. In the real world, we use copper for almost all of our wires because it does the job brilliantly and, well, let's face it, it's way more abundant and a heck of a lot cheaper than wrapping our houses in gold wire. But hey, don't feel bad for the materials that failed our test. They are called electrical insulators, and they're honestly just as important as the conductors. Materials like plastic, rubber, and ceramics act like giant brick walls. They completely stop electric current from passing through. And this totally solves the mystery of why dangerous metal wires are always wrapped up in colorful, safe plastic. The plastic acts as an insulator, keeping the electricity trapped inside so it protects us from getting a nasty shock.
Well, we have definitely uncovered the incredible hidden world of electricity today. But I want to wrap up this explainer by leaving you with a really thought-provoking scenario. Imagine waking up tomorrow and your entire town has suddenly lost its electrical power for 2 whole days. What are the things you literally wouldn't be able to do anymore? Think about everything we covered today, from your fridge to your phone to that simple little flashlight. I really encourage you to look around your home today with a totally new appreciation for the magic of circuits humming behind the walls. Stay curious, everyone.